Okay, as we look here, radioactive isotopes and half-life. So we're going to be talking about some half-life material today. And as you can see up here, right here by the image that we have here, this looks like a carbon-14 is changing into a nitrogen-14. So once again, the atomic mass is not changing, but the atomic number is going from 6 to 7. So that's telling me that a neutron is being changed into a proton during this process. And this process is the beta decay process. Now, for this to occur, I can see here that it's telling me that it is approximately 5,730 years. That is the half-life. So in order for half of those carbon-14s, which is an unstable compound, to become a more stable nitrogen-14, it's going to take 5,730 years. All right? So when we're talking about this half-life, all right, what are our learning targets? Well, we need to be able to calculate half-life of a radioactive isotope. How are we going to do that? We are going to examine the rates of the nuclear decay and be able to calculate the half-life of the radioisotope, the age of the object using radiochemical dating, and finally, how much of the isotope remains. So we'll be going through all of those three things today. So in order to hit that learning target, we're going to need to be able to perform this success criteria. Excuse me. Radioactive elements are unstable. They decay and change into different elements over time. Now, as they are decaying, okay, they are unstable, they are decaying, they are changing to a more stable element. As they're doing so, this takes a certain amount of time. Sometimes it's very, very long, and I'm going to show you here coming up where some half-lives are in the billions of years, where others could be fairly quick. I've seen half-lives in the seconds. All right? So these occur over time, and that time can vary greatly. Okay? Not all elements are radioactive. Those that are listed below are some of the most useful for geologic dating of fossils. So maybe a geologist finds this fossil and says, hey, I want to figure out how old this fossil is. Well, how old is the Earth? Anybody have any idea? I haven't checked that for a while. Okay. I'm going to say a guesstimate 4.5 billion years old. Okay. I'm going to just guess at that. I'll look that up later here. But nonetheless, these fossils, okay, uranium-238 has a half-life of 4.5 billion years. Maybe that's where that 4.5 was coming from. Okay. Potassium-40 has a half-life of 1.25 billion years. Carbon-14, we discussed that earlier. It has a half-life of 5,730 years. So when we talk about the definition of the half-life, okay, that is the amount of time it takes from the unstable radioactive element to become the more stable element. It takes that many years for half of that to occur. The half-life of an element is the time it takes for half of the material to decay. I just told you that. Okay. Each element has its own half-life. So, half-life is the time it takes for half the material you started with to decay. Each element has its own half-life. And this decay happens in pairs. And what do I mean by that? One element is decaying into a more stable element. So the unstable element is decreasing while the more stable element is increasing. So as one of those go down, the other one is getting greater. So in this instance here that we've been talking about, the radioactive isotope carbon-14 is decaying into nitrogen-14. So as my amount of carbon-14 decreases, my amount of nitrogen-14 will be increasing. So I could compare, and that's what they do, I can compare the ratio of carbon-14 to nitrogen-14. And once I see that ratio, I can determine how many half-lives we've been through. The half-life of each element is constant. It's like a clock that's keeping perfect time, meaning those are not changing. The carbon-14's half-life is always going to be 5,730. Not going to be changing between one carbon atom to the next. Now, let's see how we can use the half-life to determine the age of a rock, a fossil, or another artifact. So if I'm looking at this right here, the blue grid represents a quantity of carbon-14. As you're going to see, each time I'm hitting my clicker, it's going to change, and I'm going to have less blue and more red. But down at the bottom here, as we begin, notice that no time has gone by and that 100% of the material is carbon-14. Okay? Now, you're going to see later on, we're going to do a carbon dating activity, okay, coming up in the next week or so. And you're going to see that in order to do this carbon 14 dating, we have to have non-living materials. All right? So, for instance, we could have a spear that we could want to date. Well, actually, the spear could be part of a tree that's dead. Okay? It's not a live spear. Still not doing photosynthesis and stuff like that for the tree. It has to be dead. So, at the time that it became non-living, okay, I have 100% of the copper-14. So we notice that as no time has gone by, 100% of the material is carbon-14. So my ratio, 100% carbon-14, 0% nitrogen. So there's no ratio because I don't have any nitrogen. Now, as I'm looking here, I can see that I have 4 times 4. So I have 16 boxes there. In order for my first half-life to occur, I'm going to take half those boxes and convert them from blue to red. Boom. Oh. Boom. All right. So now we have our first half-life. So now 50% of it is carbon-14, 50% of it is nitrogen-14. My ratio is 1:1. So I know that after one half-life, that is 5,730 years. So it took that long for half of the carbon-14 to decay into the more stable nitrogen-14. Now, I'm going to go through another half-life. Now notice, I don't have 16 blue boxes anymore. Now I only have 8. So what's half of 8? 4, right? So I'm going to see that 4 boxes have now been converted from carbon-14 to nitrogen-14. So in my second half-life here, my total percentage left is 25%. I have 4 blocks out of the 16. That's 1/4, 25%. So I have 12 blocks out of the 16 that are red now. So 75% is nitrogen-14. And my ratio now is 1 to 3. Now down here at the bottom, when it's reading, I've gone through 2 half-lives. So what I need to do is I need to take that 5,730 and multiply that by 2 to get 11,460. So in 11,460 years, now I only have 25% of my carbon-14 left over. 75% of it has been converted into nitrogen-14. Now I'm going to go through one more half-life. So this is going to take my box number, blue box number, down to what? 2, right? So when I do so, my blue box number is down to 2. So 2 out of the 16 are blue. So that's going to give me that 12.5%. Okay? 14 out of the 16 are red. So that's going to give me that 87.5%. When I did my math, it came out to be 1 to 7 ratio. 1 carbon-14 to 7 nitrogen-14s. Once again, to determine the number of years that went by, 3 half-lives, so I take 5,730, multiply that by 3, and that gives me the 17,190 years. So after that many years, only 12.5% of the original carbon-14 remains. The rest has been decayed into nitrogen-14. So if we look at that ratio, okay, the ratio of carbon-14 to nitrogen-14, we can see these percentages, and then we can take those percentages and then we can make them into ratios, and we can see how many half-lives have occurred, and therefore we can actually give a date to how old that particular substance is. As I'm looking at this is just the chart, and I'm not going to worry so much about these numbers here of grams. Okay, we'll talk about that in a little bit. What I want to talk about here is the percentages here. So when I went from 100 to 50, that was 1 half-life. So that's what it's signifying here. Then half of 50 is 25. Here's another half-life. Half of 25 is 12.5. What's this number going to be down here? It doesn't have it on there. What's half of 12.5? 6.25. So right over here, this line is 6.25. That would have been 4 half-lives. And you can see how it's affecting the mass of the carbon. Went from 10 to 5. Half of 5 is 2.5. Half of 2.5 is 1.25, etc., etc. Now, what we call this type of a curve, we call this exponential decay. So I want you to write that down in your notes so that you understand. Exponential decay. You've probably talked about exponential growth when you were in biology, and that was a J-shaped curve, okay? That was a J-shaped curve that went up exponentially. This one is just the opposite. It is going down exponentially, so we call it exponential decay. On this slide, here's a little bit different because on the bottom, on the x-axis there, we have time as in millions of years. And on the y-axis, we have percent parent isotope remaining. All right? So as I'm looking at this one, I can see that my half-life is right here, my very first half-life. So as I'm looking at that, from 100 to 50, okay, 150 took a million years, 1 million years. So that's telling me that my half-life is 1 million. Okay? My next half-life comes right here at 25. That was 2 million. My third half-life here would be 3 million. Okay? That's going to happen at that 12.5. But once again, the graph is representing exponential decay. Now that leads us into our calculating half-life. Okay? So we're going to do some calculations with the half-life. What you need to do is I want you to get this equation into your notes. So go ahead, I'm going to pause my recording. Now in this particular equation, AT right here is the amount left over after T years. So that is going to be, usually we're going to see these in masses. So that is going to be the amount of the unstable isotope that is left over. The A sub 0 here is the initial quantity of the substance. So that's how much the substance was at 0, okay, at 0 years. The T up here, that is the number of years that have went by. The T1/2 right here is the half-life of the decaying radioisotope. Okay? So, as I'm looking at that, I'm going to pull up an equation, or excuse me, a sample problem. So I want you to go ahead and write this sample problem in your notes, and then we are going to work the problem. Okay, carbon-14 has a half-life of 5,730 years. How much of a 144-gram sample of carbon-14 will remain after 1.719 times 10 to the 4th years? So I could have that number in scientific notation. I can have it in a normal notation. Does not matter. What does matter is that I plug the right numbers into the equation. So I'm going to start out with my A, T. That is what I'm trying to find. How much of the sample of carbon-14 is left? My A sub 0 is going to be 144 grams. My 1/2 is there, and now I have T over my half-life, the T to the 1/2. So that is going to end up being an exponent. So I'm going to put my T up there, 1.719 times 10 to the minus 4th, and that's going to be divided by my half-life, 5,730. Now I'm going to use that to get my exponent for the 1/2. What do I put to the half power? So I'm going to start right there. So how I'm going to start is I'm going to take 1.719 times 10 to the fourth. Ooh, I wrote negative fourth there. 10 to the fourth. Okay, let me get the fix here. And I'm going to divide that by 5,730, and that gives me 3. So basically, I'm taking 144 grams, 1/2 to the third power. So what is 1/2? It's 0.5, right? So I'm going to take 0.5 to the third power, and that gives me 0.125. I'm going to take that 0.125 and multiply it by 144, and that gives me a value of 18.0 grams. So I have 18.0 grams remaining after 1.719 times 10 to the fourth years. Here is our next example we're going to work. So go ahead and write this one down. Chromium-48 has a short half-life of 21.6 hours. How long will it take 360 grams of chromium-48 to decay to 11.25 grams? So what I need to do, ladies and gentlemen, I'm not going to use my equation. Okay? I'm not going to use my equation. What I'm going to do is I'm going to start here with my 360. And I know that half of 360 is 180, right? So when I undergo my first half-life, I go from 360 to 180. My next one will take me to 90. My next one will take me to 45. My next one is going to take me to 22.5. And then finally, I'm going to hit that 11.25. So I know that in order to go from 360 to 11.25, I need 1, 2, 3, 4, 5 half-lives. How long was each half-life? 21.6 hours. And I have 5 half-lives. So when I take my 21.6 times it by 5, I get 108 hours. So it's going to take 108 hours to get that 11.25. Now, I'm going to show you something else here too. 11.25 out of the 360, that's going to give me 0.03125. So that's 3.125% that I have left over after those 5 half-lives. All right? Now, I'm going to show you something here too, folks. Here's one half-life. Here's my second half-life. Here's my third half-life. Here's my fourth half-life. Here's my fifth half-life. Okay? What's 1 times 1 times 1 times 1 times 1? 1, right? What's 2 times 2? 4 times 2. 8 times 2. 16 times 2. So 1/32. I guarantee you when I divide out 1 divided by 32, it's going to give me this number right here. Okay? So I have 1/32 of the carbon, or excuse me, of the chromium-48 left over. Questions on that? All right. We're going to do one more here. So go ahead and copy this one down, then I'll work it. If I have 800 grams of technetium-99 and it decays to 100 grams of technetium-99 in 639,000 years, what is its half-life? So once again, I'm doing this just a little bit differently. I need to figure out if I have 800 to start with, and I'm going to 100, how many half-lives is that? So my first one's going to be 400. My second half-life is going to take it to 200. My third half-life is going to take it to 100. So I know that I have 1, 2, 3 half-lives. Now the total amount of time to get from 800 to 100 was 639,000. That was the total time, and I know that I had 3 half-lives in that time. So if I take 639,000 and I divide that by 3, it's going to give me 213,000 years. And that, ladies and gentlemen, is my half-life. Okay? So my half-life is going to be 213,000 years. And just by looking at it, I had 3 half-lives. So I have 1, 2 and 2 is 4 times 2 is 8. I have 1/8 of my technetium-99 left over. Could you tell me what percentage 1/8 was? I hope you can. Okay. What is it? Anybody do the math? 12.5, 12.5% left over. So that means that the more stable one would have been what, 87.5%? All right. Any questions on this?